All right, welcome everyone. Thanks for coming to my talk, Templates Made Easy with C++20. In this hour we have together, I'm not going to make the templates easy at this moment, but going to kind of show you how things are evolving and get you excited about how code can look a lot more like normal code than it used to with templates, and we don't have to teach some kind of archaic magical tricks to accomplish some of the same goals if we're using modern C++20. I'm Roth Michaels. I'm a principal software engineer at Native Instruments. And before I get into a little bit more about myself and what I do, I want to just kind of say a little bit of a thank you to the Include C++ org, both for this version of the talk and previous versions of the talk I gave. I had some questions, ran into some interesting stuff. Actually asked ChatGPT for help that told me crazy answers, and then the real humans did help me out. You can ask me in the hallway about that story later. It's pretty funny, but I'll tell you the short part of it is, the first part of the answer, ChatGPT told me why, when I asked like, oh, why does this work? C++ templates are really complicated, is what it said. And also, the other reason I'm bringing up Include is that the first time I attended a C++ conference, I went to a panel on diversity and inclusion organized by Include. And one of the things that I was inspired to do at that panel was to encourage other people to come up and speak when I'm speaking. So whether any of you in the room or watching online now, or maybe later on YouTube, if you've never given a conference talk before, there's nothing particularly magical about me or any of these other speakers, but all of us have interesting stuff that we might have learned and have something to share. I encourage you to try it out. Lightning talks are maybe a friendly way to join. That was my first talk, giving just kind of 5 minutes of silliness. And if you're nervous or want help writing an abstract, the Include C++ Discord is a great place to reach out for help. Or just email a speaker that you like and ask them if they'll help you out with your abstract. People have done that for me before. So we get kind of as many opinions and stories in our community being told. I encourage everyone to think about giving a talk in the future. Anyway, a little bit of background about me, because this will kind of relate to some of the things I'm talking about. I'm a principal software engineer at Native Instruments, which is a music technology company. It is a combination of companies that have merged together. Actually came from the company Isotope, and we also have Plugin Alliance and Brainworks. We make both hardware and software for dealing with digital audio, for both mixing and mastering albums, producing beats, DJing, post-production for film and television. You know, basically, if it makes sound, we play around with it. And so later in the talk, you'll see some of the examples involve audio, and that's what I'm drawing stuff from. But don't worry, you don't need to understand any signal processing for these examples. They'll just kind of be really simple and illustrative. So why did I want to give this talk? It actually goes back to when I first got this job and was being interviewed by my hiring manager, and she asked me my favorite interview question, which I have since stolen and asked in any of my interviews of C++ developers, which is to rate yourself on a scale of 1 to 10 on your scale of C++. And then I tell them, before you even tell me, the number doesn't matter, but say the number and then tell me what's one thing that you know that someone more junior than you doesn't know yet and you could teach them, and then what's something that you don't know yet that you want to level up and learn more about. And that answer to the second part was almost always the same, whether it were recent grads or more senior folks. Something about templates. Maybe they might say template metaprogramming, partial template specialization, or SFINAE, substitution failure is not an error. If you don't know what that is, we're not going to really talk about it too much, but we will show some examples in this talk. But essentially, certain constructions with templates that won't make sense just basically mean nothing's generated, and that template is just kind of out of the picture. We'll show some examples of that, and we'll see why we don't need to kind of worry about those arcane magic tricks. And also, shortly before we upgraded to using C++20 on our teams, I was helping a more junior developer with a problem that he needed to solve that actually SFINAE was the answer for, and I didn't want to just tell him what letters to type out. I was actually trying to teach him, how does this work? But he had a meeting in a little bit while, and I tried my best. I think he sort of got it, but it was really tough. I just thought, oh man, we're almost done with this compiler upgrade. In 3 months, I could have taught you something much simpler and easier to learn and a little bit cooler. And also, it's to get you all also excited, if you're not using C++20 yet, to thinking about, hey, is there a way I can do this? I know there are technical challenges, maybe if you're doing embedded things that use a weird compiler, and even if you have no restrictions and build everything from source, I've been through it as well. There's other challenges like, well, you got to deal with your CI infrastructure, OS updates, etc. But hopefully that gets you excited about this topic. So let's dive in. The kind of core piece of templates and why they're in C++ is generic programming, and we'll see how that leads to other things, and that leads to this kind of another nice feature we have now that has evolved and gotten really awesome by the time we get to C++ 20, which is Constexpr. So this is our journey from templates to Constexpr. So very basically, templates allow us to write generic functions like standard find. So in this example, we have a string, hello world, our classic string in message, and we want to find the location of the comma in this string, because I'm ones that like the original KNRC book that puts the comma there and no exclamation point. And we can do this with characters in a string, or we can take a vector with numbers in it and look for 42, and we have our exact same find function, and it's going to work in both cases. And this is implicit and deduced, but really these are templates. The first one is find searching on cards. The second one is find searching on ints. And this is going to work with any basic type, any of your types. It's just you write one function, and it's going to work for any types that kind of allow you to search from beginning to end and look for values. So that's what it was for. But along the way, Erwin Unruh, and I'm sorry if I don't know how to pronounce that name, I've only read it, not heard someone else say it, discovered, I read by accident, but it sounds like he was probably doing something on purpose, so I want to give him more credit than that not only can do this generic programming, but templates are also Turing complete. And this first kind of implementation of this was writing a program using templates that actually didn't compile, but the error message kind of was the result in the program. And when I was preparing for this talk, I actually thought, oh, it would be really cool to write Lisp in templates to kind of prove to you that it's Turing complete, because if I can write a Lisp, I can do anything. I started working on it, and I thought, this is really hard. I don't think anyone really wants to see template Lisp at a C++ talk, but maybe someday I'll do a lightning talk on that. I'm not going to I'll show some examples, but not really explain all the details of metaprogramming and how that works with templates, because that's a multi-hour topic on its own. But if you want to learn more about that, I highly recommend you check out this talk by Walter Brown. I believe it's in 2 parts, and this is the first part of it. But let's take a little bit of a look at what template metaprogramming looks like and why we might not need to do that anymore. So for various reasons, as a musician and composer, I have a lot of interest in the Fibonacci sequence. I always thought it was cool when I learned about it in middle school. And so if you don't know about it, this is the sequence. It's basically take 2 numbers, add them together, get the next one, and the next 2, 1 and 2 equals 3, et cetera, et cetera. Some people consider a 0 starting at the beginning. Fibonacci actually didn't put the first one, but it kind of works out the same. I consider that first one the first Fibonacci number, the second one the second one. So when I'm talking about this algorithm, I'm not 0 indexing. But if you do want a 0 index, we'll see that there is a kind of 0 value in this code. So this is what a Fibonacci algorithm looks like as a template metaprogramming program. And you'll see in orange this we have this struct that has a value variable member. And you see the way that we have this notation, the static assert, the Fibonacci, and we're passing 6, so we want to get the 6th Fibonacci number, : value. That : value is saying essentially that's our function call in metaprogramming, and we want to, that's our essentially return value of the meta function. And so the way this works is we have one normal kind of recursive function that takes as a template parameter the number of the Fibonacci number we're looking for. We have an assert so that we're not going to deal with getting into negative numbers and blowing up this algorithm. And you see that this is all kind of going to create this Constexpr value, and we're essentially going to recursively call this and start basically instead of starting with 1 + 1 = 2, 1 + 2 = 3, we're going to start at the calculating kind of back down the other way in this recursive algorithm. And we see we'll stop at our 2 base cases. So when we ask for the first Fibonacci number, that'll be 1. And then so that when we get down to 0, we just return 0. So that like I said, the 0 index could be that imaginary 0 that you saw on the first slide. And that's kind of how this algorithm works. But Yeah, you can do this, and this will all work at compile time, and that's the real magic there. But we got this feature in C++ called Constexpr. And instead, that allows us to write this Fibonacci algorithm like a normal function. And now instead of this : value, we see parentheses like a normal function call. We see the Constexpr, and since we put a constant value in there, this can all run at compile time. And hey, if you don't like templates, these days we also have auto parameters and functions. And so you can just push auto there, and now we don't have any templates going on, and we have a function that can run at compile time. And in C++20, we could also use consteval, which would mean this could only run at compile time if you want to be really, really sure about that. And then, hey, we can make this a little better maybe. Instead of a static assert, what if we want to make it like impossible to pass negative numbers to this? We can use, this is a sneak peek of something coming later. We could add a concept. So instead of just saying auto, we can say, well, this auto can be anything that is an unsigned integral. So just remember that. We're going to kind of come back to that concept in a little bit. But when Constexpr first came to the language, it was kind of very basic, could do some really limited things. But by C++20, it got really cool. You can actually allocate memory inside of Constexpr functions, just as long as you clean it all up afterwards. It can't, you can't allocate memory to compile time that somehow still exists later on your user's computer when they're running your program. And that allows, you can also now have Constexpr vectors and strings, so it gives it, you can kind of work more like normal programs. And also kind of another concern people have is when you have Constexpr, that doesn't guarantee that functions at compile time, just maybe means it could be. So in C++20, we now have consteval. That means like, oh no, this can only be at compile time. Frankly, I think most of the excitement and power myself is in Constexpr, but it's good we have consteval. I don't know if anyone noticed, I actually called it Constexpr/Constexpr in my title, which should have said Constexpr/Consteval. And that just shows you I'm actually, myself still mostly using Constexpr, even though I was very excited for Consteval to get into things. So that's kind of, how we can, instead of using templates or metaprogramming, you see that now instead we can use Constexpr and we write normal functions that look like normal code. Another way we can make our code more easy to read is a new C++20 feature called fold expressions. Now, a fold expression allows us to take something like this, a function that's going to take a sum of an arbitrary number of types and arguments, and they're going to need a plus operation, and it's going to sum them together. So you see this, the ... of our template parameter pack with the class there, and then our args, that is the multiple arguments that could get passed in, and then we put this ... with the plus and then the args. And what that allows us to do is essentially, instead of writing some kind of recursive algorithm to do this, it allows us to kind of say, oh, I have some amount of arguments, just put them together and put pluses in them. So what this template will generate, if I pass in sum 1, 2, 3, 4, which should equal 10, this will generate a function that looks like this. So we'll take 4 integer arguments and it will add them together. A plus B plus C plus D. Now, something to keep in mind is there's 2 forms of this. I can put the dots on the left, or I can put the fold expression dots on the right, and there's associated with this. And the way I kind of remember what happens if you put it on the right or left is essentially just thinking about like what direction are we going to splat out this ... args. So when I put it on the right, you see that we essentially we put it on the left, stage right, we will start unpacking these things and applying the operator to the first 2, then the next one and the next one. And if you put it on the right side, it starts working from the other direction. And so that one would look like this. And what this is really nice is that before we had fold expressions, anytime you dealt with a variable number of template arguments that you want to apply some operation to, like summing, the only way to do that was pulling them apart with a recursive algorithm like this. So you see that we have 2 overloads for sum, one that just takes 1 value. So if I just pass in 4, I'll just get out 4. And this other recursive one that will take 1 argument and then some number of other arguments. And you see it just keeps calling sum again with the rest. And so we're recursively doing this. Nothing really wrong with recursion. I mentioned earlier, I'm a fan of Lisp, so popping things off fronts of lists is kind of, what you do as a Lisp programmer. But if all I want to do is do A plus B plus C plus D, or maybe E and F, it just looks a lot nicer in the code, I think, when you're able to just say, oh, dot, 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 splat these all out and put pluses in them. We'll see some other cool examples how we can use this with metaprogramming later with functions, but this is just a really nice feature that makes your code kind of a lot easier to look at. But not only that, it actually will reduce the number of templates that actually need to get instantiated in your program, which could speed up compile times potentially, although I've seen benchmarks that can kind of go either way, number of size of things, et cetera. But because in this case, every time you do that recursion, that second sum is going to generate a new function, one for 4 arguments, one for 3 arguments, one for 2 arguments, and then the top sum. So we're generating 1 function instead of 4 in this case. So that's also kind of a nice improvement. So earlier I mentioned that this is kind of the star of the show is concepts. When I earlier had that example where I constrained our auto to being only unsigned types. And so if you've maybe it's been around for a few years now, so it might be something you've heard of, but I'll kind of show you what this looks like in kind of where you can put concepts, and then we'll actually talk about what they do and what they are. So imagine we have some function foo. I don't know what it does, but it takes function template, I'm sorry. It takes 2 function template parameters, the t that represents the argument to foo, and a class u that's the return type of foo. And when you write it this way, those could be any types. You don't know, but maybe foo doesn't work with all types, and you want to actually narrow that down. Just one small aside, you'll notice in all my slides I use class instead of type name in the templates. These are both interchangeable. This is a personal taste thing of mine. One, for slides, I get to make it bigger for you if I use less letters. Also, in this case, you can interchangeably use class and type name. There's other places in C++ where you can only say type name. And so I like to save type name for that. It's a personal style thing. I used to think the complete opposite, but just keep in mind, class, if you've not seen this, doesn't mean class type. It's a little bit weird, but it just really means type, or type name in that case. But instead of having a template that can work for any type, we can actually do a lot of things to constrain how this works in various ways. We can say, instead of just being any class T, and any of these C1, C2, C3, C4, C5, those are all names that we're assuming is some concept we've defined. And if you don't know what that is, in a few moments we'll actually see what I mean by concept. But first I just want to show you all the places you can put, just think of it as a way of constraining some type. So instead of saying class, we can say C1, and so now T can only be things that are a type of C1. You can also put these requires clauses after the template parameter list, and where we see C2, and this allows us to take the types that were provided in the template parameter pack and use them in some other template. We could actually apply some other operations on that T, but that's another place you can constrain the T is after that. Instead of having a specific template or an auto, we can have a concept name and then an auto, and this will mean our return type is going to be constrained to that return type. Where C4 is, we can constrain, as you saw earlier with the unsigned integral, we can apply a template concept constraint to any of the parameters of a function by putting a concept name and then auto. And then also we can put another requires clause at the end of the function declaration. And the use case for this is, let's say I want to find something out about if that X, provided you do some other operation, does that satisfy the constraints of the concept? So in this case, imagine there's some other function bar. I want this foo to only work if you call X bar with X, the type returned by that satisfies whatever this magical C5 is. And so that might be like, oh, we know we're using bar inside this function in a certain way, and we want to make sure that's true. So if you've not seen concepts before, you might not feel like you understand this yet. It's okay. I just want to show you throughout the examples, you may see them appear in one of these 5 places. So let's look at a real example so you can see what it's like to use concepts and actually write your own concepts. So this is a little silly example. I'm going to write a function for dividing something in half called half. And I have a overload set where essentially I have a template that is going to do if those were integers being passed in, that would be an integer division by 2 rounding up. I didn't really think about negative numbers in this example, so don't worry about that too much. The actual math is not the important part here. And then I have 3 more overloads for dealing with floating point. I have one for floats, one for doubles, and one for long doubles. But we can make this work a little bit better. So if we're looking at this example here, yeah, we see that this is the one that's going to work for anything. These are our double overloads. But instead, we can actually put this all together into a single function by using a, so this is actually not putting, you can also show in this example, I'm using, actually, I'm sorry, we're not at the, it's not a concept yet, we have a type trait here, but there is also a integral concept. I think maybe old demo reasons I used the type trait there. But the interesting thing you'll see in this example, which is also something else I wanted to illustrate, is that I'm using this if Constexpr. So what this is doing is saying, well, if it's true at compile time that t is an integral type, do my kind of round up divided by 2, and if not, do the other one. And something important to keep in mind if you've not used if Constexpr a whole lot, and this might confuse people, is that people say, oh yeah, with if Constexpr, only the true branch has to compile, and the other one doesn't. It's not exactly true. In templates, you don't have to worry about valid code in the other blocks. But if you use if Constexpr in some other context, it all has to be real and compile. I know that confuses a lot of people. I've had people come up and ask me, hey, why is this if Constexpr like putting me an error here? And like, well, it only gets that magic of making code disappear if you're in a template. But I'd like to ask for some audience participation. Don't worry about going to the mic. I'll shout out your answer to the, just shout it out and I'll repeat it for folks online. But does anyone see a problem with, like, you know, we're talking about numbers, but what if I put, you know, some other type in here that would cause a problem with this algorithm? Yeah, like if I put std file system in, that's not going to make my file path in half. It's just going to, I don't know, put /2 at the end. So that's not really what we want here. I really want this to be a function that only divides things by half. So what can we do about this? Well, maybe instead of this if Constexpr signal function, we'll go back to overloads and try out concepts. So in this example, we see that I have 2 overloads for a half. Oh, I'm sorry, this was a typo there. Ignore that extra mass after the plus. I decided to write this in a more normal way and I must have forgotten to fix that slide. I apologize for that. But you'll see I have 2 overloads, one that takes a, it says std integral auto, and the other says std floating point auto. So that std integral and std floating point are concepts. And so it's saying, yeah, that auto take any type where it's true that it's an integral value or it's true that it's a floating point value. And so, great, now we've solved the problem. We can't put std file system in here. We'd get a compile time error if we did. But this probably isn't good enough. There might be other things that are neither integral or floating point that we would want the half to work with. Any ideas what might else be wrong here? Yes, custom types. So what if I have a strongly typed unit type, like in my case decibels, and I want to divide that in half? I'm going to get an error saying, like, oh no, you can't do that. I'm like, yeah, but my type has a slash operator, and yeah, it does division, and so dividing by 2 will divide by 2. So let's make another modification, and we can still use something. So now you're going to see how you can make your own concepts in this example. So I'm going to define a concept called can/half, which is going to determine whether this type can be divided in half. And so there's a few pieces to this. It's actually, concepts are also another kind of template in themselves. So I say template of some t, but instead of saying class or defining a function, I'm saying it's a concept named can/half. And then I have this, what's called a requires expression, where I'm saying I require that if you have some lowercase t of type capital T, this must be a valid expression. That is the requirement that t must be divisible, like it might be legal to go t divided by 2. And if you do that, it must, the result must be the same type as t. And so now, this will work for my custom types, and then we can further refine this so that if you can be divided in half, and you're an integral type, we'll use a second overload. And if you can be divided in half and you're a floating point type, you'll use the third overload. And so that's concepts. And maybe, I know we should take some questions at the end on the mic, but just before we kind of get into some other stuff here, if I just want to, anyone have any quick questions or lost or kind of... Okay, I think we're okay. Now we can look at something scary. So if you're just, as you're writing these requires expressions, there's a little bit of trouble you can run into. So watch out for this easy mistake you can make. So this is kind of a silly example that I was working on. This is actually related to the one I had to ask ChatGPT, and it told me templates are hard. But a different internal version of this talk, I was making a very silly kind of contrived overload set where I want to take things that have a plus operator for concatenation, like strings, and use that to add them together. But if it's an arithmetic type, I don't want to use the plus. I want to concatenate them by putting them into some other pair or vector or something like this. And if they're ranges, I want to concatenate the range. So this is a concept where I'm defining that I want to be able to concatenate two things with the plus operator as long as they're the same type, they're not arithmetic types, and they're not ranges. And so the way I've done this is saying that, like, for some A of type T and B of type U, they should be able to be plussed, and something comes out. And they can't be, it requires that they're the same. It's required that they're not arithmetic types, and it's required that they're not ranges. Notice that there's an underscore V there, because that's actually a type trait, not a concept. They're like our floating point integral. I don't really know why there's not an arithmetic concept, but ChatGPT will tell you there is one until you ask, are you sure? And then it will apologize and say, no, there isn't. But notice how I put requires before all three of these. And this is really necessary because this is what it's saying. It's requiring that those concepts are true. A common mistake you might make if you're doing this is write this instead, where you just put the concepts in there without the requires. And what this means is that's valid code, that you can instantiate that template that way. It doesn't mean any of those things are true or false. It just means like, oh yeah, you can put T's and U's into that. Great. So this is what you need to do in this case. But to avoid that mistake, you actually probably don't want to use anything that's requires inside of another requires. Really, if you want to, the kind of best thing to do is, if you want to combine a combination of existing concepts with your own custom requirement, you should do it like this instead. Instead of putting them all inside as a list inside your requires, you can use Boolean logic. So you say, okay, these two things must be the same. One must be, we can't have it be an arithmetic type, and we can't have it be a range, and you have to add them together. So if you ever see yourself using a named concept inside of a requires block, you probably don't want to do that. Instead, you actually mean and them together with your requires block. And you won't notice until you get bugs, because this is just going to compile just fine. So why do we want to use concepts in our code? Like, how does this actually make our code better? The kind of most exciting part about it for me is documentation. Because when you have a T, or class T, or class T, class U in some template, like, you don't know what that, like, you can put in there. And if some of you have, like, actually misused some templates, or even, past a range of floats to find, but, past a maybe integer, it might say, like, oh, I don't know what kind of find to use. Concepts can really help with that. So we're going to show some examples with a concept I call in-place processor. So this is where we're getting into the DSP examples. This is actually a concept we have in our code base. We had it as a philosophical concept before we actually wrote, code using modern C++20 and templates. But an in-place processor is kind of a generalized form that reusable pieces of digital signal processing code can take. And they have two main APIs. that these processors will have. And this is an example processor. All this is, and don't really worry about the DSP in these examples, but what this one does is essentially it's called the inverse processor. It's basically going to take all the values in your DSP, and if they're positive, make them negative. If they're negative, make them positive. And so what the API for these in-place processors is they are some function that calls process, and it takes a span of floats that it's going to do some operation and potentially modify, or just analyze those floats. In real life, it's not a span. It's actually usually probably a multi-dimensional situation, because we might have stereo audio or surround sound audio, so we don't have just one set of floats. We have multiple sets of floats, one for each ear, but it makes the slideware a lot easier if we just think it's a span. So this is a little bit of a simplification. And if you're interested, MD span is not really a great fit for audio, because we want to actually have a whole lot of different layouts of the data that are type erased, but that's a hallway story if you want to ask me about that. The other key API with these processors is potentially the ability to reset some state. So the inverse one has no state. It says, give me numbers and I'm going to flip them around. This is an example of a very simple filter that will take, if you have some sound, it will take all the higher frequencies out of my voice and kind of make the sound lower if my voice is passing through here. The math doesn't really matter. Don't worry about that. But the key thing here is that you'll see that there's this previous value that's getting stored as we're doing this computation. And imagine I'm mixing some record and I'm playing it along and this filter is being applied, and I stop and go back to the beginning. That state from the music over here isn't what should be playing through anymore at the beginning. So I need to somehow get myself back to default when I hit stop and rewind and want to listen to my track I'm mixing again. So we need some ability to reset. So that's basically the two functions we're dealing with here. Process some floats, reset to default state. So we might have some situations where we're going to take processors that wrap some other processor. This is just called wrap processor. That's going to do some pre-processing and some post-processing, but this is actually a super common pattern where you'll compose some general utility inside some other process. Note, I've gotten people ask me questions about this, that I'm using a shared pointer to pass in the thing I'm wrapping. That's not really relevant for this. There's reasons you might do that. There's reasons you might pass it by R-value reference. You might pass it by pointer, but that's not really germane for our story. What you'll see here, I'm taking a template that's saying I'm going to take any type of processor, or really I call it processor type instead of T to try to make it more clear. We have a comment saying that processor type must have a process method taking a span of floats, but it's just a class. It can really take anything. So that's not really a great thing for documentation, just a comment. We can maybe look at it a little better with a static assert and a type trait. So we can assert that, this type trait in place processor V on processor type must be true. So how would we make that type trait? It looks something like this. We got a lot of stuff going on here. Funny little things when you haven't seen them for the first time. Standard false type, you're inheriting from false, and we have this true type. What's this void T thing? Decal type, decal val. And then our process, there's a lot of parentheses and stuff going on. And this other Constexpr bool, don't worry about it. It's a lot of stuff to explain when you're teaching that to somebody. Instead, with concepts, we can write this beautiful thing like this. It just says, in-place processor requires that I can write code like this. That's the really nice thing about writing your own concepts, is instead of doing some magic to prove something's true, you just say, I want to write code like this with this type, and give me an error if it's not true. And once we have something like this, we can now place this concept in our template parameter pack, and we see that now the processor type, we will get a compiler error, and I'll show you some examples of those later, where the in-place, so we can only take things that have a process function. But if you notice, this wrap processor maybe has a problem, because the first, we got this reset here, but the filter had a reset, but the inverse processor didn't have a reset. So this is kind of maybe something people have complained about C++'s concepts versus Swift's Similar facilities in languages like Swift and Rust is that even though I'm forcing you to only put in things that have a process function, that doesn't mean I can't go Wild West and call any other silly function I want, like the reset. So, because you see, the concept doesn't say it must have a reset. It must have a process, but I told you some of these need to have a reset as well. So what can we do about this? So there's kind of two neat little options. I really like this trick of using if Constexpr to make some code disappear if it's not going to be valid. So in this example, I'm saying at compile time, I want to, if this is true, that I can use one of these requires expressions to say, okay, assuming some processor type P, I want to be able to call P reset on it. If that requirement is valid, then yeah, the if Constexpr will be true, that code will exist, and I can call reset. If I put in the inverse processor, I can't call reset on that, and then reset will just have an empty body, and we've solved the problem. Or maybe we want to actually pipe that API difference up to our wrap processor. So another variation is we could actually make the whole reset function disappear if we want to. So in this case, I'm saying we're using, if you remembered, you could put a requires after the function. And this is saying I could have a named template here, but I'm using one of these requires clauses after the requires expression. So I'm saying we require that this requirement is true, that processor type P has a P reset. And if that's not true, then that entire reset function is going to disappear. Another kind of quick example I'll go through is, this is a very common thing is that we have in our code base and a lot of DSP code bases is we want to like do something on some blocks of data. And so we have some input, some output, and it's a general thing that's going to take the input, call a function on it, and give it and put it in the output. But this standard function is no good for real-time DSP code because standard function can allocate memory, and we won't get into it in this talk, but allocating memory is non-deterministic in time. So in a real-time context, you can't do things like that, and so you should not be using stood function here. So normally instead, we'd make this block processor have a templated process function, and then we'd take in any type there and usually pass in some any lambda type instead, and then we're not going to have any allocations. But we could pass in 42 there, and you can't call 42 with our input floats. So let's try to constrain this with a concept. So instead, we can say, okay, we're only going to allow the third argument, and this is using a standard library concept saying this is only going to be allowed if we can invoke this process function with a span of floats. And so that's going to make sure that we're only passing things in that are kind of a callable lambda object that's going to work on those floats. Oh, but if you don't like looking at templates, again, concepts can also be used with auto. We can put this like this, and all of a sudden, this just looks like a normal function, just like our original standard function version, but it's actually a template, and it's actually forcing us to only pass in callable objects that are going to work in this context. So, kind of putting all of these bits together, fold expressions and the concepts, Constexpr, I'm going to show you a very brief metaprogramming example. So a few years ago, I gave a talk at CBPCon about a graphics library that we use internally and how we wrote a layer on top of a property system that allowed us to do things like set colors and fonts on things. We could do it in C++. We could do it with graphical tools, editing the UI. We can serialize those things to XML files, use style sheets. And we had all sorts of ways of doing this, but all those things like XML, it's going to be runtime. And we had a lot of runtime errors involved. So this talk was about putting type-safe compile time wrappers around that. And we did this all with SFINAE and other metaprogramming tricks. And I got called out on YouTube after I gave this talk. Why didn't you use concepts for this? Two reasons. One, we wrote the code in 2018. We'd recently adopted C++ 17, so we had no concepts. And by the time I gave the talk, concepts were around, but I had not used them personally too much, so I wasn't 100% confident my concept slides would be right, so I didn't put them in. But I use them now, so I can show you what this looks like. This is going to be a very, very reduced example of how all this works. The real property since it's much more complicated, but imagine we are defining some property on some UI object by creating a struct called size that will describe that property. And it will have three things. It will have a type for the property, will be float. It'll have a name that we can use for serialization. We'll call that the string size. And we'll give it a default value for when the widget's initialized, and we'll say it's 100. And then what we can do with this is we have this mixin class called hasProperties that takes a list of types, and each one of those types will be one of these structs defining a property. And on construction, it will call this addProperty function for each one of the types. Now this is a really cool thing and my favorite feature of the fold expressions. So instead of using fold to like add stuff together, the operator I'm using here is the comma operator. And then and I need to put this inside of parentheses. And so what this is essentially saying is for every type I passed for my template parameters, call this addProperty function once for each one of those types. And you'll see when that happens, it will take the name and the default value, and it's going to put them in this defaults dictionary so we know what the defaults are. And so this works nicely for size. But what if we did something like this? Now, I know I said earlier standard string is Constexpr now. When we wrote this library, it wasn't. So in some situations, we actually need to make default value a function that would run at runtime because it couldn't be Constexpr value. But in this example, you might look like it could be, but just assume like we have needs for this to be a function, or maybe the name might need to be a function because we need to format it like we're having an optional property of some t, and we need to format it like that. So we need some way for this to work where instead of assuming name and default value are member variables, we want this to work if they're a variable or a function. And so the way we could do that is with concepts is we can make a getName function that is if Constexpr, we require that name is a function we can call. If so, call name. If not, we make the assumption that name is there and it's just a member variable and we just return that. But what would this look like in my actual code base that was written before concepts? I'm sorry, actually, I'll show you that in a moment. I have another example here of how we do the default value in a very similar way. We can say, does it have a default value, requires this, and we can make a get default value. And then this one's a little more complicated because for the default value that's not a function, we want to make sure we're also checking like, let's make sure it has default. So we have a default value function requires that's true, and then has default value requires that it has a default value member and that it's the same type as the type member. And then that allows us to have these two functions, get default value constrained on has default value function that we'll call the function, and one that does this. So you can do this with overloads or the if Constexpr are both moves available to you. So this is kind of an alternative way of doing this construction. And so now you see instead of assuming they're variables, we can call our functions and it will do the right thing using our concepts to figure out what's going on. And before I show you what the old code looks like, we're going to run into one more stumbling block. What if I didn't put a default value here for border width? Because maybe I assumed it would just be 0 like a default float would be. Well, the way we've written this so far, since there's no default value, we're going to get an error. And it looks like a lot of error messages. Don't read all of this, but here's the cool thing about error messages with concepts. The word because shows up here a lot of times. So instead of seeing like, this didn't instantiate blah, 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 it's actually telling me exactly what's going on. It's saying, because size doesn't satisfy default value function and it doesn't satisfy this. So it's actually kind of telling me exactly what's wrong with my code. So I'll need to add one more thing. I'll make another third version of get default value for things that are default initializable. And this is another standard library concept. So I'm going to be able to say, this function will work for default initialized types. And so for our border width, when there's no type and it's default initializable, I can just default construct it and I'll get 0 and that'll be great. But now that I've written this also works for size where I did say a default value because floats are default constructible. So this one's going to get called, or default initializable, but this one's going to get called. But I don't want that. I want it to be the 100. So this is the other kind of neat thing about templates, is that you can make them more specific. So this is the least specific one, saying, okay, if the type T type is default initializable, use that default construct it, but only do that if it's default initializable, and we also require that it doesn't have a default value member and it doesn't have a default value function. And so now our size one will not call this because it will trigger those things in that orange requires clause. Now, what does this look like in the old code with SFINAE? I'm not going to explain how all this works. I'm just going to show you how much code you have to write and kind of how not great it looks. So we have first to make a type trait of ours. So we have has default name function, and we still have our if Constexpr again, and our void t, etc. This doesn't look so bad, but to handle that default value case, we got to write a lot of this stuff. And so we have to teach people how all this works. The code's a lot more complicated, and the errors really aren't that great. So, concepts are a really nice way to write this code where we don't need to use SFINAE anymore. And I do wonder, do we still need to use SFINAE? I was asking people about this. I heard there was at some point like a name mangling thing, and like maybe it mattered in GCC, but that I think has been fixed. I have not reached for SFINAE once, I think, since using concepts. If you do know cases where like SFINAE is like the bee's knees and you still got to go for that, please find me in the hallway afterwards, because I'm actually curious for those examples the next time I'm talking about this. And one last quick topic before we close. I want to talk briefly about how you can make sure you're using concepts correctly or in a more useful and safe way using TDD. So I'm not going to explain TDD, but normal TDD is this loop of you write a failing test, write the minimum amount of code, make the test green, and repeat this loop. I'm suggesting when you're dealing with concepts and templates, you should add a few more steps in between. And the reason is to avoid this mistake of the reset, where you can call functions that are all outside of your concept. And so if you take this, it takes a lot of discipline, but if you take this TDD approach, it will make sure you don't accidentally do this and call functions or access members or do other operation, and really any operation that can't be done on the type of your concept. So we have a few more steps, and I'll show you what they look like. So this kind of longer loop of the concept TDD is, first you write a minimal concept, like for your processor. And the easiest way to do that is like saying like template class T concept, my concept equals true. And so that concept, we're starting, basic TDD, that's going to always be true. We'll start with that. And then whatever type you're using in your unit tests, like some made up type to test with, some test class, you put a static assert in there to say, your assert that T matches our minimal concept. And we start off, okay, that's going to be true. That's okay. Start with that. Maybe to see it fail, you can make the concept false first. And now step 3, we're going to write our first failing unit test. And we want to start, as you know, start just enough code to make the test pass. But anytime you're going to use that type T, you've got extra TDD style steps to do. First, before you write any code, you're going to add whatever construction with operation on T, however you're using it, you're going to add that to your concept you made in step 1. Then when you do that, your static assert will fail because your T probably doesn't have that member or function yet. Then you'll make your test T conform to the concept. And now you can write the code in your real function that uses T. And if you haven't written the minimal stuff for it to pass, you repeat the loop. And so that this ABC is our little safety net if you're very disciplined for the concept work inside of 4 and 5, 3, 4, 5 being the normal TDD loop. So very quickly, what does this look like? So before writing the minimal code to make, I imagine I have some unit test that tests that reset works. Before writing the minimal code for this, I'm not going to put that reset in, comment it out yet. Like before we write any code, I know I want to type reset. First, I'll add reset to my in-place processor concept. And now this is our actual concept we use in our code base where it has process and reset. Now, this static assert that our test T is an in-place processor will fail. Now that that's failing, I can now put in the reset and things pass. And so, I kind of recommend that approach. And in conclusion, all of this stuff we put together allows metaprogramming and other compile time running code to look like normal code. And this is something that is getting better and better and better over time with C++, that we can have all of these powerful features, move more stuff to compile time, do more metaprogramming. Obviously, when reflection comes, that's not going to look like normal code maybe right away. But this looks like much more like normal code. And hopefully this has gotten you more excited about the kind of nice way your code can look using C++ 20. And so if you got excited today, please go see Nikolai's talk later in the conference, where I think he's going to teach you a lot more about actually how to use these concepts and templates that I've just been teasing you about. So thank you very much. So what are your questions? Well, I'm sure everybody 100% understood everything, but at least I hope you got excited. Like I said, this wasn't to actually fully teach you these concepts, but kind of show you the kind of nicer way our code can look in the future. And also, it's not just writing this stuff. The really nice thing about this is library code. So a lot of the developers I work with are not necessarily writing templates day to day, but a lot of library code I have written or colleagues have written that they use templates. And so now they will see nicer error messages, and they'll actually be using library code that looks like normal code, and they're not going to be seeing all this arcane magic that they don't understand in the headers, or don't really understand how to code review either. But looking at this kind of concepts and Constexpr and fold expressions, this is going to be code that most developers on your team, I think, are going to be able to code review. So thank you very much. And if no one wants to ask any questions at the mic, please feel free to talk to me in the hallway if there's anything you'd like to know more about. Oh, is there an online question? Oh, super.
Hi. There's one question online from Stefano Kaisa. What are the compile time costs of concepts as compared to old style?
I think some of this, I have not done a lot of benchmarking on this. I believe some of this stuff can surprise you. So I know I saw a talk on some other things, not necessarily concepts, but like the fold expressions. Strangely, those like you'd imagine be faster, but like at certain sizes, the old techniques actually become faster. And this was a few years ago, so this definitely is like changing as compilers evolve. But in general, the consensus is concepts should be faster, because if you're using SFINAE and type traits, you're actually instantiating many templates, potentially get that job done, and you're not doing that. You're not instantiating all these template structs, or actually generating structs and functions and inline variables. So theoretically, it should be faster. I personally have not done a lot of benchmarks, though.
Sure. One more question from Sylvian Drubert. Could you use stud invoke to call either a member or method for default value? Wait.
Oh man, this is why pair programming is like. I'm just trying to think about what's so. Just trying to make sure I understand the question. Oh, yes, you could. That would be another way to do it. I think, that was another option. I was just kind of wanted to demonstrate writing the requires clauses, but you should be able to. I believe I guess kind of just the way my brain works. I've not written it that way, but I don't see why you shouldn't be able to use the stud invoke with an empty parameter list. That should totally work. Yeah, because that's the stud invocable. The arguments you're putting in there is saying that those are going to be the function arguments you invoke with. So if you had empty, because actually the way that's working when you're doing this is actually that concept actually has an imaginary extra type in the beginning. That's the process function that gets put in that template. So yes. For the default value one, I could have, instead of doing my requires thing, I could have just, and making my own has default value function, I should have been able to say, oh, no, I'm sorry, this is why it's, nice to pair with actual computers. No, the issue there is, so in the stood invocable case, I'm saying that this is something that has a function call operator object on it. So I can take whatever the object I pass in and call it directly, versus in the other case, I'm, but what you could do, so there is you could do, I think it'd be a little bit hard to read, but what you could do for the default value one is I could have defined this has default value function as stood invocable, and then the type, and then inside the angle brackets, do decal type of t : default value. So that's saying the type of whatever t : default value is that invocable. So that would work, yes.
Thank you.
Yeah, I should have had maybe Emacs up to actually type that out, but hopefully you were able to read that. And feel free to send me an email if you want me to type out that example for you, whoever asked that question online. Please.
Hi, thank you for the talk. I have one remark about the Fibonacci function, because I tried to do the same thing as you did, and I found out that doing it with template metaprogramming actually works during compile time with, for example, fib of 45, and doing it with Constexpr ended up to the compiler taking until infinity, yeah. And I even needed to supply some extra arguments to let the calculation take that long, yeah. So it was like aborting after 2 seconds or something, and then I put in some extra parameters. So yeah, because I wanted to also use it as an example, like you did, and I was very surprised to see that it failed in Constexpr or consteval context, but with TMP it worked, and in GCC it worked way better than in Clang. I don't know why.
Oh yeah, well yeah. So yeah, that is something I kind of glossed over and cheated with just because I like Fibonacci numbers. But yeah, so what's going on here is that there is a maximum recursion depth that will happen at Constexpr time, and different compilers have different defaults, and as you said, there are flags that let you turn that up. So if you want to do crazy stuff, you can turn that up, and it could take a while. But with the it's not exactly the same. You're not actually calling the functions at compile time in the metaprogramming case with templates. You're just like creating a template that's creating a variable each one at a time, and you can do that forever. So yeah, for these kind of things that we would go really high in recursion, without change, if you don't want to change those compiler flags, actually the ugly template metaprogramming one might be the better option. But yeah, maybe I should find another example that isn't something that could go infinite like that. I just like Fibonacci numbers. But thank you for bringing that up, so people should know about. So if you ever do hit that limit, there are flags in your compilers that you can make it go more. I've run into that because actually I don't normally write recursive stuff that's going that big with Constexpr. But yeah, that is definitely an issue to be aware of. Thank you.
Okay, yeah, and the other thing where you had the decimal, the extra, the half implementation of the decimal, you could have also just added another overload, right? But yeah, it's there to prove another point, because yeah, that's making a template is just upping the complexity, while just solving the problem would have also been solved by just adding another overload, right?
Oh, yeah. So actually, another intro talk I gave that's actually online now that I gave at C++ on C this summer, I was pointing out that, yes, if you can use normal functions as overloads, you should always prefer those over templates. Yes. This is like I did in the original example. So this is just there to show you how I can further constrain the Ken half. But yes, actually the better thing for the floating point ones, in my opinion, would have been to just stamp those out as float double, long double, as I did before. And the integral one, I guess you could do as well with overloads.
Yeah. Okay. Thank you.
Hello. Thank you for the talk. And my question is, would it worth migrating old code to use the new concepts and stuff, considering the advantages are obviously less code, but what else?
Yeah, so another talk I gave at CPCon this summer was about dealing with legacy code, and one of the things I did advocate for is stuff that works and is not causing you problems. might not have a whole lot of business value to go around messing with. So I do have a branch where I've started doing some of this stuff because I would like it to be more readable and maintainable for my colleagues in the future. So that is an advantage. I think the code will be more maintainable, but if it works and no one's touching it, it's a trade-off. So I think it has nice. It could potentially have compile time advantages, but you really don't, with any performance stuff, compile time or runtime, you don't know until you measure. So like I said, in this case, actually, I do want to make those changes to this GUI library, but over the past couple of years, the business value has not been there versus other kind of more important missions I could be on. So I would encourage you if you could find the time, but legacy code that works maybe is sometimes left dragging sleeping.
All right, thank you.
Hi. I know this is not really the topic of this talk necessarily, but one downside I've been struggling with is tool support with these, and I'm wondering if you think concepts might kind of tie things up and make proper tool support for templates in general.
What kind of? I'm not sure what you're meaning by tool support.
Well, I mean, since the contracts are much more weaker, right? So like if you're subclassing, there's a much more clearer path between two things. But if it's a template, when the contract is just basically like, it has this function, it makes things harder to, find things in a large code base, for example, like, oh, is this call happening somewhere? And I'm wondering if concepts might help in that regard, maybe?
Oh. It would be nice. I don't know. I have to think about that, but off the top of my head, I feel like I've been trying to debug that situation before where, and I'm, only thing I can think of, which is a bit crazy, is either writing some like Clang tidy or other thing that will go through your entire code base, find every type in it, and then generate code that would test every type for every concept, and then you would know the places in your code that have those things. But so yes, you could probably make some crazy tools to do that. But so far, my life has been that's probably kind of similar on the debugging front. But it's kind of interesting idea, though. Hopefully, someone watches this and gets excited and makes something like this.
I really do, because it's when you combine it with template parameter, deduction, when it's sometimes the code you look is not really the thing, so it gets really hard to the only thing you can end up doing is just doing a find on all files, like a text search or something. Oh, is this function getting called or something? But yeah, I'm hoping as well.
Yeah, I mean, often what I'm doing is when I'm trying to figure that stuff out is actually just doing stuff like runtime debugging and putting it in there and seeing what types are actually showing up when I run. But yeah, I hadn't thought about that too much. It would be nice. I think there's maybe some opportunities, but nothing that I'm aware of at the moment.
Thank you.
I think we're probably out of time for questions, so thank you very much, everyone.